Okay, so I'm just going to do another video on some more lldb bug weirdness stuff, a little bit of a follow-up to my last one, where so lldb has this bug where if you have some like handwritten assembly code that for some reason like pushes a pointer on the stack as kind of passing an argument, and then in the callee that receives that pointer on the stack, if you do a finish command while broken in that callee function, lldb will kind of blindly just like read the stack looking for a return address and take basically any pointer, anything it finds, and just try to write a hex cc there. And so in the last video, we showed being able to pass a regular data pointer on the stack and then have lldb write a breakpoint into the data and corrupt some data and stuff like that. And so I actually implemented a fix for this in lldb and submitted a patch and stuff, but my fix only is pretty simple. It basically just requires the memory that's pointed to be executable for lldb to continue setting the breakpoint. And that's kind of one little like check or heuristic that's pretty straightforward and makes sense. But it doesn't completely remove buggy behavior, because if a pointer to code is passed in the same way, and that check will pass. And the situation this might occur in is if you have some handwritten assembly that for some reason is doing this thing where it passes an argument on the stack for some reason, which does happen, which I've seen happen, and that pointer is also a like pointer to code, and so it's a function pointer. And so in this very niche situation where you have some handwritten assembly that's for some reason pushing a pointer on the stack to another stub, and not using a call instruction to get into that stub, and then you do a finish command in that stub, lldb will have this kind of will continue to have this buggy behavior. Well, it finds this thing that could be a return address, but actually isn't. It's just this argument that's been passed, and lldb will write a breakpoint to that code that was at the function pointer that was passed. And so I've been playing around with trying to reproduce this behavior, and I've kind of done it, but I've also uncovered some other weird stuff, and so I'm just going to do this video to document it a little bit. So basically, I have my little test setup from last time. I'm using the one with the small C++ entry point stub that just calls into this assembly. My func is written in assembly, and that's over here, and just returns the return value from there. And what I've done is I have this, my stub with non-standard stack layout, stub, and it's being jumped into, and it's being passed a pointer on the stack from my func. And previously, I just allocated a stack variable and pushed the pointer to that stack variable, and then stub with non-standard stack layout received that pointer to the stack variable in my func's frame. So this time I changed things, and I introduced this new function. It's called random func, and it's kind of at the bottom here, but it's just a random function basically, and we are going to pass a pointer to this function into stub with non-standard stack layout. And so I'll just split things. So yeah, and this is going to simulate this thing where we are going to get, or passing a function pointer. And so this is how I'm doing this. You can't directly move random func into RDI on Mac because of some relative, like absolute addressing is not allowed or something. for 64-bit, and so you have to do this at got.pcrel thing. That's not that important. The main thing is that like RDI contains a pointer to random func, or contains the address of the first instruction in random func after this instruction. Then we just push it onto the stack and then jump into our stub. And then the idea is that if we're broken on the stub and we do a finish command, lldb is going to find that pointer to random func, and it's going to think it's the return address. It's not, but it's going to think it is, and it's going to write a hex cc into random func's code, the first instruction. It's going to basically replace this first nop with a hex cc trap, and then it's going to continue execution. And what I've set up is the stub is going to pop off the RDI from the stack. It's just going to clean up the stack from that that argument, and then jump into my func cleanup, which basically I'm just going to kind of comment out this code. In the base version of this code, my func cleanup just called the random func, and so it actually doesn't even need to do this. So let's just return, and we'll make, and then lldb main break stub. And so what basically is going to happen is we're going to finish here. It's going to write the breakpoint, and we're going to continue execution. And since random func is never actually called, the program is just going to finish. And we're not going to see the debugger just like trap or like breakpoint, because my random func's never getting called, so that a hex cc that was written in there is never going to actually get executed. It's just going to live there. And so if we just run, and then if we do a finish from stub with non-standard stack layout, it just the program just finishes. So now the idea is that we're going to call random func, and so now kind of buggy behavior is going to appear where we never actually set a breakpoint on random func, but all of a sudden we're going to finish, and then the debugger is just going to break for kind of randomly on random func. And that's because of this underlying bug where it wrote the CC into random func kind of accidentally. And so we'll rebuild it and then rerun it. And then now if we do a finish, we're expecting to see finish x51. It's a little bit odd, unexpected. Let me go back to the code I was originally doing. So this is the code we just added. If we let me just try this. Finish. It's okay. It's maybe it's because of the pop RDI. I also added that and kind of changed some stuff. Yeah, and the pop RDI was kind of a last minute thing I just added, and this is kind of getting at some of the weird behavior I was seeing. So anyway, yeah, so I've removed the pop RDI. So now it just pushes this thing, it does nothing, and then calls into my func cleanup, which does nothing, and then calls random func, and then I'll explain the or racks thing later. But then it just calls random func, and so we're expecting that we'll finish in the stub, and then it's going to come through and call into random func, and then we're going to see this kind of random. The debugger is going to kind of randomly break here in random func, even though we never set a breakpoint there. We can just confirm that with our breakpoint list. We're only broken on stub with non-standard stack layout. So we'll come here, we will finish And here we go. We've just kind of randomly hit a breakpoint in random func, even though we never set one. We can also kind of try something which, and well, so we've broken in random func, and if we think about what really should happen, if we do a finish command in stub with non-standard stack layout, really all of these quote-unquote functions here, I guess mostly, yeah, well, I guess myfunc, stub with non-standard stack layout, and myfunc cleanup, they are really just part of like one function because we're not using any call or returns in between them. We are purely just jumping around, and so they are effectively the same function. And so if we do a finish command while in stub, we would actually expect it to completely finish the execution of kind of these collection of little assembly snippets that comprise like the one myfunc function essentially, and then we'll break back out when we're back in the main, which was the caller of myfunc. And so we randomly break in random func, but and kind of you might think that's like right because we did this finish command, and then so we kind of break, somewhere here, but that's actually not correct for it to break in random func. That was a little bit of an unclear rambling, I think. But yeah, so basically this is incorrect. It just kind of, the bug is that we are kind of randomly breaking in random func. And one thing we can do to actually kind of really further illustrate this is, so we can globally expose this symbol and come here. So then we can change things like so, and we can call random func from our C code or C++ code. Yeah, so random func, and then we'll remove the call here. And maybe we'll just add a ret to keep it simple. So now our myfunc is really just not going to do almost anything at all. I guess we need to clean up our stack. Maybe just add 8 RSP. Okay. And so the C++ code is going to, then we'll call myfunc. So now, basically, we're going to call myfunc. It's going to push this function pointer onto stub thing. We're going to do a finish command in here. It's going to set the breakpoint in random func, and we're basically just going to return. And so now execution will go back to main, and we'll continue. Then we'll call random func. Then we'll call random func, and the breakpoint will kind of hit out of nowhere. The idea is I want to illustrate that there could just be like arbitrary amounts of code. Here you could be in myfunc. You could be in myfunc and you're stepping along, and then you're in that stub, and then you do a finish command, and then the program like the program just keeps going because maybe it never actually executes that function that the breakpoint was written into, and so it just arbitrarily continues execution, maybe for like a long time, like an hour or like a day or something, and then like a day later, it's going, and then it finally something calls random func, and then all of a sudden there's like a breakpoint in the debugger. Like that's not like a realistic example because you're not going to just be leaving a program running in your debugger for like days at a time probably. But the idea, I'm just trying to show that an arbitrary amount of time can pass in the program before we actually observe the behavior of this bug, which is that the debugger is just going to randomly break out. And so let's try this. I've actually never even tried this before. So yeah, we relinked our C++. And so now if we run, we're broken in the stub, and I'm expecting that if we do a finish command right here, we're going to then immediately see it breakpoint in random func, and if we look at the backtrace, it's going to be from main. So finish. Oh, I was wrong or something. Okay, I was wrong. It just ended up running. Did random func even run? So one thing I was doing was we could just insert a crash into random func just to check if it was even running. Finish. Yeah, we got a crash. So random func was definitely running. So yeah, well, I don't know. This is actually kind of I don't understand why this is happening. But that's kind of the whole point of this video, is because I was seeing a bunch of stuff that I didn't understand. So this is actually kind of consistent in some way with some of the weird behavior I was seeing, which I will now explain. So let's just forget I did any of this stuff. We're just calling my func and then returning the return value. Let's forget about that. Let's forget about this stuff. So before we had this, we were calling random func, and we were seeing a breakpoint happen. So let me just go back to where we were. Run, and then finish, and then yeah, our breakpoint hits. And so one thing, so in my original code, or one thing I noticed is that, oops. So if you add, so one thing, I had this add instruction here, and I was, let's see, it was something about cleaning up the stack. And so we push something on the stack here, and that thing on the stack remains, and we're now here, and we call into random func, and it returns back. And then so now, yeah, in order for this code to be correct, really, we need to have this add here to clean up the stack. Actually, if we continue in the debugger, it seems to work, which is kind of odd, actually. Oh, that's interesting. So yeah, so basically, in order for this code to actually be correct, we need to clean up our stack here, because we've pushed this thing onto the stack, we've done some stuff, and now we're exiting this routine, and so we need to remove that thing from the stack. We do this by adding, and the reason and so what I was expecting is that if you forget to add this, for example, the code, say code does not clean up its stack, I would normally expect this to crash, because when the return happens, the program is going to pop some thing from the stack and then jump to it. And typically, you have data on your stack, or at the very least, code pointers and stuff. And so that's going to cause a crash, because you're just going to try to jump into some data or something like that. But in this very specific scenario, our thing on the stack is a function pointer, and so this is actually not going to cause a crash, because the return is just going to kind of basically pop that pointer and then jump to it. And in fact, that function pointer is random func. And so in practice, what's going to happen is that random func is going to get called twice. It's going to call here. It's going to go do its execution, and then it's going to come back down here, and then it's going to get called again because because the pointer to random func is still at the bottom of the stack. We forgot to clean up, and then effectively return is going to jump to random func again. And then the reason it all seamlessly works is that then the random func is going to, for the second time, execute, and then its return instruction is going to go back and return to main. And this is I literally just realized this. So that was a little bit of a tangent, but that's just why that just started. That's why forgetting to clean up the stack here continues to just works, effectively just works. But basically, the original stuff I was seeing is that so we call random func, and then for our code to be right, we should clean up our stack. But what I was observing is that if we build it again and run it and then finish, the breakpoint never gets hit, which I don't understand. And that's why I made this video. I don't understand this, and so I wanted to document it. It's very odd because this is code that occurs after the call to random func. And so my understanding of how everything is working is that stub, we do a finish here, and it writes a breakpoint into random func. That means the next time random func executes in any kind of way, the debugger is just going to randomly break on us, or trap, or have a breakpoint raised, and we get our command prompt back to do stuff. That's what's going to happen anytime random func is executed at all. And so that's my assumption. That's my understanding of things. And then our execution is going to go, it's going to return, it's going to jump to my func cleanup, it's going to do some naps, and then it's going to call random func. This should always, our breakpoint is sitting in there, and so we should definitely see a breakpoint raised in the debugger. But that did not happen. We finished, and the program just exited. Which is very curious. We can actually further investigate this. We can enable the breakpoint logging, and so we'll run this. This is some additional logging where lldb will print out where it has set its breakpoints and stuff. And so we're at our stub, we do a finish. Breakpoint says that this F94 address is where it put the breakpoint. This was the top of our stack. So that's F94 is the first instruction of random func. And if we can just confirm the image lookup via this thing, and it says random func is the symbol there. And so so our logging shows that it put a breakpoint in random func. But then then it just the program just finished and did not do anything. And so that is just really peculiar to me, why that would happen, because this code, because the difference is whether or not this add RSP is here. If we recompile and run it again and then finish, we get the breakpoint. We can try it again. Finish, we get the breakpoint. But then we uncomment it, we add it back, and we finish, and we do not see the breakpoint at all. It's very mysterious, because this should not affect whether the breakpoint appears or not. This is code that occurs after the call, and so yeah, like we should be able to do arbitrary stuff here. We could do whatever we want here, and it should not be able to affect whether we see that breakpoint or not, because this is all happening after random func is called. But for some reason, this stack adjustment after the call is changing things. It gets more interesting. So originally, this was like a bug, but I had my add RSP above the call, which is not really supposed to be how it works. But I saw the same behavior. That shouldn't actually really affect things, whether we clean up the stack before or after the call. We should still, even if we cleaned up the stack right here, at this point, random func has already had that breakpoint written into it, and so when we call random func, it's just going to push this address on this address of this OR instruction on the stack, and then jump into random func and hit the breakpoint. But let's rebuild, and then go, and then finish. And again, program exited with status. We're not seeing that breakpoint get hit. And yeah, I don't understand this at all. My theory is that there is something related to the stack unwinder here, and lldb is doing some kind of analysis of the instructions in the program or something like that, and it's doing some kind of analysis, some kind of static analysis on these instructions, and looking for operations that change the stack. And if it finds them, somehow that changes the way it works, and somehow bubbles down to whether we see that breakpoint or not. But that's my theory. Some kind of analysis is being done here that analyzes whether the stack is being adjusted or something like that. I don't understand it. But that's also somewhat consistent with that thing earlier in this video where I had this pop RDI here, which I had not tested that before the video too much. And that's also an adjustment of the stack. And that also caused us to not see the breakpoint, if I remember correctly. And so if we rebuild again, we have none of the stack adjustments in the code. We should see the breakpoint, finish. Yep. So now we'll just add back this pop RDI. It's effectively doing the same thing as this add RSP. And oops, rebuild. And then finish. And again, we do not see a breakpoint being hit. So that's as much as I can really say about it. I have this, I have this feeling that there's some kind of analysis being done on the instructions, and it's related to the stack unwinder, and that influences whether the breakpoint is hit or not. I think this is all kind of buggy behavior. And so kind of all bets are off, I guess, because we're writing a breakpoint to a kind of a random piece of code, and I'm not sure lldb is kind of built to, handle this or something like this. This is not how finish is supposed to happen, really. And so one last thing, I guess I'll explain these OR things. And so I was curious, I wanted to make sure that this code was even executing at all, because my theory was that my theory was that originally that we have this breakpoint here, it should always cause the debugger to break out if it gets here. And then I wasn't seeing the debugger break out when it got there. And so I started to wonder, well, maybe somehow this code is not even executing at all. And so I've been using basically the exit code from the program as my kind of like way to see what's going on in the program. It's kind of the easiest, most minimal way to get some output from the program. Like I don't really feel like dealing with syscalls and writing like text or anything out of this program. I just want to kind of observe kind of how the execution of this program is going. And the return code is probably the easiest way to do that. And so basically racks is where so when you have like when you have like return something in the main, that's just basically that's the number that appears with the exit status code. And from the assembly point of view, racks is what is used for that. And so you put your return code in racks and then return, and then that's going to appear here. And so basically, just to kind of test where execution has been going, I have this code here that ORs the low bit into racks if it reaches here, and then ORs the second bit into racks if it reaches here. And that's why we see this 3 here, because both of these are being hit, and so it's ORing both of those bits, and we're getting a 3 here. I don't really know why there's a 5 here. I'm actually never really properly initializing racks in this entire thing, and so the 5 is kind of random. But this is how I was able to test and confirm that no, like random func is definitely executing. It's setting this low 1 in racks. Otherwise, otherwise the return would not be an odd number basically. And so if we just quickly rebuild this to demonstrate, run finish or continue. Yeah, now it's 62. It's and so this is how we can if basically if the exit code is an odd number, we have confirmed that random func is running. So it's definitely running, but the mystery is that why is it not breaking out, even though it's definitely running, and we're pretty confident that there is a hex CC that has been written into its first byte. And I guess the last thing I'll show is me trying to confirm this more deeply. And so, again, we can't use the debugger to check if there's a hex CC here, because when we do this finish instruction, execution is just going to continue. Well, actually, maybe we can. I don't know. What if we? Yeah, wait. Maybe I'm being silly. What if we set a breakpoint on my func cleanup, and then yeah, wait. Why? This actually could definitely work. So we do our finish here. Now we're broken into my func cleanup, and now let's examine the first 4 bytes of random func, which I guess is here. Just as random func. So this is actually kind of interesting. We don't see. So maybe I was right all along. So the idea I was thinking of is we put a breakpoint here. Theoretically, the debugger has written the breakpoint into random func, and so actually in memory there's the hex CC. And then what if we just broke here and then disassembled it and saw if there was a hex CC here? And it doesn't say there is, but I actually think this is, the debugger's not showing you the actual literal state of the program's memory address space right now. the program random func doesn't actually contain a hex cc there. It contains a nop there, and so the debugger is actually going to detect if it has a breakpoint there, and then just not show you that. It's going to show you the original code, and so that's why. Okay, so that's why this wouldn't work. So I wasn't being silly. So basically, I wanted to come up with some way to like side channel leak whether there was, well, one step back. So basically, this just demonstrates that we can't really use the debugger to examine things very well here, because we're kind of examining some very debugger internal kind of stuff that's happening. And so using the debugger will maybe like hide, is going to kind of hide things from us in some way. Like it's hiding the fact that there's actually a CC here, just showing this nop, because that's what's actually in the binary. But like literally at this moment in the debugged process, there is a hex CC living in that memory. And so we need to find another way to kind of leak what's there. And my idea was to also use this our exit code like channel basically, and what I just thought to do was in my func. So I'm just going to delete the breakpoint this too. So my idea was in my func cleanup, our theory is that at this point the breakpoint has been written into memory, and so what if we literally write some code that just reads some memory, reads the memory of the first few bytes of random func, and then sets that in the return code. And so what this does is it again moves the pointer to random func into RDI, and then just dereferences that and reads well, I guess 8 bytes to be precise, into racks. And then yeah, we don't need this. And then what if we just return? And so the idea is that well, this is actually going to, we need to also make sure to clean up our stack. Otherwise it would call into random func. And so now this is just going to put, we're going to do the breakpoint, it's going to write the CC, and then now it's going to read the actual true state of what's in memory and random func, move it into racks, and then return. And then hopefully in our exit code we should see, really we're only going to see the first byte there. Even though we read 8 bytes here, on maybe on definitely on Linux, on Mac also, maybe in POSIX in general, even though it's an int type for main, only I believe it's only the range of return codes is like 7 bits or something like that. And so really we're only going to see like the first byte, 7 bits, because if it's negative it means there is an error or something like that. And that's how like segfaults and stuff, like segfaults will have like a negative return code, I think. But anyway, let's try this. So we can rebuild it and can run it. And let's see, I'm expecting, what am I expecting to see? So we do the finish, it's going to write the CC, then it's going to continue execution. We're going to read some memory, put it into racks. It's basically just going to take the low byte, so I think that's going to be the first byte because of little endian. And then, so we should just see a racks of CC, and then we'll see, hopefully, a return code of CC. And we don't. We see 90, which is the nop. So that is very interesting. And I think it's because, actually, we cleaned up our stack here. So what if we just don't clean up the stack? I don't understand this at all. What if we just don't clean up the stack and then do this? So now we're here, and we, yeah, so now we broke in random func. Well, that's interesting. So we broke in random func because, yeah, we have no stack adjustments here, and so this is just like that thing we were looking at last time. However, what if we did load some stuff of racks into, we did load a few bytes from random func into racks. So what is racks? Racks, yeah, the low byte is CC. And so that actually does reveal that the CC was definitely there, because otherwise, see, random func has 4 nops and then some stuff. So we have 4 nops. That should be 4 90s. But here we have 3 90s and then a CC. And so that that in kind of one way is our side channel. We've truly confirmed that there was a CC in memory there. And our breakpoint did get hit. And so, yeah. But for some reason, if there's these stack instructions here, it doesn't work. I can try one more thing. So, yeah. So one I guess I maybe say that a lot, but one last thing we can try is that what if we just load, what if we just load that into racks, and then have that be the return code. And so we load it into racks, then we call random func. So racks should be hex cc at this point. We call random func. It's going to do nothing. Don't worry about it. That's not even, that move is not really even necessary. It's going to OR in the low bit into racks, and so it'll change it from like cc to like cd or something, and then we'll go in. Then it'll return back up into this code, and it'll OR in the 2-bit. I think it'll change it to like cf. So add 2, and then it'll return. So I did try this once before. I think it should work. So here, finish. So our breakpoint did hit. Continue. But yeah, cf. But what was interesting is that, so we've confirmed that the breakpoint was in memory, but we also did hit the breakpoint. And so now, but that's because we did not have any stack adjusting code. And so now, maybe lastly, we'll add back the stack adjusting code. This should, for whatever reason, make us not see the breakpoint. Well, this should, for whatever reason, not make the debugger break back out again. But hopefully we can still leak the fact that there was actually a breakpoint instruction in memory. And so we run, we finish, and we have a 93. Very interesting. So maybe, I don't know, maybe this did confirm that actually we should actually, so maybe this did confirm that there was a nop in memory. So maybe we should really just double check. So it says it's writing a breakpoint at this address. What is that address? It is random func, right? What if we increase it by 1? Would that show random func plus 1? Yeah. So that is definitely random func. So the logging, yeah, so it's not like it was writing a breakpoint somewhere else. The logging definitely shows that it was writing a breakpoint. And so to the exact instruction, to, oops, whoa. Yeah, that is the start of random func. So let's clean this up one more time. So finish. It wrote a breakpoint. It said it wrote a breakpoint to the first instruction of random func. And then continue execution. We read random func, put it into racks, and then add a couple bits to it if those execute. And so basically what this return code of 93 tells us is that a breakpoint was actually not written into memory like the logging said it was. It remained just a hex 90, and we executed both random func and then went back because we ordered both of those bits in, and then returned. And so yeah, that. But again, if we just add, if we remove the stack adjusting code, let's see. So F9E was where it wrote it last time. So let's run it again, finish. Huh, okay. Oh, interesting. F9A. Oh, wait. So now this time F9A is where it wrote the breakpoint, but it is also, but we also just added, we also just removed some code from the program. And so, yeah, so this is still the first instruction of random func. And so it's a different address, but it's still the first instruction of random func. So it's saying that I wrote it there. And then, yeah, and then we're seeing it actually hit. And then if we look at racks, it contains the first. Let's see CF. Wait. Wait, that is interesting. That means we're actually like here. So what happened, and actually this is also interesting, we have two hit breakpoint things, but this first one, it says it's like blah, 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 hit breakpoint stopping. It doesn't actually stop. It keeps going. And then we hit this breakpoint again when we do the ret. So I think this is a bug. It says a hit breakpoint stopping, and then it does not actually stop. And it just keeps going. So this is pretty, yeah, so it's interesting that we have this CF here. Okay, what happened was we did the finish. It wrote the CC into the memory of random func. We came through, came down, we read the memory. It contained a CC. We call it, it was definitely there. We called random func. It came here one time. It did not break out here. It reported a message saying that it would stop and break, but it doesn't. It comes down, sets the low bit of racks, moving it to CD, returns back up. We resume like right here after call. It comes down, we set the 2-bit. We return again. Since we did not adjust or clean up the stack, we're going to again return back into random func, come down again, and then this is where, and then we're going to hit the breakpoint again, but then we're actually going to stop this time, which is what the second logging message shows. So let's do the finish. And so yeah, and then racks is going to be CF, which means we're actually here. Because if we truly did, if we called random func and then immediately broke when we entered that function, racks would not be CF here. It would be CC. But for whatever reason, it's not. For whatever reason, lldb does not actually break when there was still a breakpoint in memory here, which is interesting. Definitely does not seem like correct behavior to me. Yeah, so that's just something I was looking at and was confused by and remain confused by. So yeah, hope you learned something.